So great. Okay. So, hi, I'm Martin. Welcome to my talk. This is an introduction to floating point numbers. By the way, I work at PAX. This is something that we are supposed to place anywhere to represent our company and how great we are. So, some disclaimers to start with. First, in this talk, I will use floats as a shorthand for floating point numbers, not for the type. If I want to use float as a type, I will say so explicitly. The second disclaimer, this is about IEEE 754 binary floats, right? The standard has decimal floats, hex floats, much of other stuff. We will be talking about binary floats only. This is the most common one you will encounter. And since we did this, two more disclaimers. One is that we will not go into the nitty-gritty details. We won't be talking about the hardcore numeric stuff. We will be talking about this as users. We want to understand why it can be weird, not necessarily how to write our own floating point unit and what can we do in there. Okay? Now, the issue with floats is that it's often unintuitive. Let's look at some examples. Like if we write this assert, 0.1 plus 0.2 equals 0.3, then it will fail. This doesn't make sense, but it makes a lot of sense actually. Okay, so we say, well, numbers are weird. So if we add 1 to 20 millions, of course, it can't be still 20 millions, right? Well, it can be. This assert will pass. And finally, if we just say, okay, this is weird, but we just found out that 20 million plus 1 is still 20 million, then 20 million plus 1 must be, still plus 1 plus 1 plus 20 million. It should be the same. No, it's not. Right? This will fail. And the thing is, this is weird. And the thing is that this makes sense if you understand floats, but most people don't because they are actually unintuitive, or rather they require you to make 2 steps in your intuition, and most people aren't taught them well. So, the goal of this talk is that after we end, you all should understand why this happens. And, you should understand how to deal with this, how to solve this in your code. Of course, this isn't just floats being bad. Sometimes it's just your tools being bad. I am using catch for this example because this is my fault. If you write this code, you say, okay, I have double A, this is 1. I have double B, which is the next, this is the smallest number that's bigger than 1. And I say, are they equal? They are not. This fails. This is correct. But this is what the testing framework tells you. 1.0 equals 1.0. This is not useful output. So this doesn't help you when you try to understand this. So what will we talk about today? First, we will talk about decimal floats. Yes, I said we will be talking about binary floats, but we will actually start with decimal floats to build understanding of floats in base 10, which is a base we are all used to and understand very well, before we start messing around with binary base. So, of course, the next thing will be the binary floats. Then we will see what IEEE 754 tells us about binary floats, what guarantees we get when we do math. And we will also talk about comparing floats, because when you have some results, you also usually want to compare with other results to find out whether this is a good or bad result. And finally, we will talk about when everything that we have just seen breaks down. Why can we just say, yeah, no, this is weird, we can't handle this. So the question is, why are floats weird? Why are they like they are? And the answer, like basically everything, is design constraints. Floats have some design constraints, like they have to be usable for computations in real numbers. You have something that's kind of like a real number and you want to do math on it. And this is really hard because there is an uncountable infinity of real numbers, which is a pain. For example, integers are dealing with just a countable infinity. This is easy. You say, okay, so I have this range. Everything that's inside this range is fine. Outside of range, I don't deal with this. It's easy. But no, we have uncountable infinity of numbers that we are supposed to deal with. Then we must support numbers that are both ridiculously huge. Like this is 2 times 10 to the power of 30. And also the equals is small, like this one. This is 10 to the power of minus 11, I think. And we have to be able to use them in the same computation. We literally have to be able to multiply these two numbers and get reasonable result. By the way, does anyone know what these two numbers are? They are from physics. So this is the weight of sun in kilograms, and this is the gravitational constant. So you literally might want to multiply these two together. And of course, we have the constraint that this has to be efficiently implementable in hardware. You know, we want to be able to do the math quickly. And when something has to be efficient in hardware, it has to be reasonably simple. It has to be fixed size. Hardware doesn't like you to just be like, oh, I don't know, I will allocate a bunch of memory and it might be like 2 kilobytes, 3 kilobytes, whatever. So
I think that you have completed one important program here. If you are using some calculation, like calculating the gravitational force between the sun and some other planet, for example, then you get to multiply this huge number with another similar huge number, and then you divide it by the distance. And if you, well, you will have to like order these operations properly. If you don't do it, you will get, well, I'm not sure if you will not get even.
I'm going to skip you because like this multiplies by another number like this, and then by this for floats. This is easy. This is actually like this is within range easily. Okay, so let's talk about decimal floats. And the reason we are talking about decimal floats, I really believe that the issue with understanding floats is that we go from base 10 to base 2, and from like real numbers to floats in one step. So we will do it in 2 steps. And actually, let's first talk about normalized scientific notation for numbers. It's a number in this form, some m times 10 to the power of n. You know, m is a real number. It has to be smaller than 10, bigger than 1, because otherwise it's normalized, and is just some exponent in whole numbers. This is easy. We know it from elementary school. Now, these are some examples. These are the first 2 numbers I used as an example. Yeah, so we see that it's actually times 10 to the power of 30 and times 10 to the power of minus 11. And it's just some random number to show that we can have many more digits behind the decimal point. I don't know. I literally made that number up. So now let's talk about fixed length scientific notation. Because what if we have only a fixed number of digits? What if, you know, we want to make the hardware efficient, so we have to fix some fixed weight. And so we will say that we have just these few digits available, mostly so it fits on the slide nicely, you know, like 4 digits, good. And when we do this, we actually, and we will say that negative numbers, we will store some bool somewhere else. We don't want to deal with this. And same for negative exponents. And by doing this, we have defined the decimal floating point. It's not useful too much because the precision is low. We have 4 digits, you know, that's not much, but it's a floating point format, right? And when we have this format of the number, again, then this first part, the x point y, this is the mantissa. In binary, this is what we call mantissa for the binary floats as well. And then we have exponent, which is the z. And this is really like basic floating point format we can talk about. Now, we can represent these numbers in this interval, minus 9,999,000,000. What's important? Notice that we have zeros here. Come on, where did I was deserted by the pointer? Sorry. Okay, notice that there are zeros here. Notice that we don't go all the way to the fixed number of digits because we don't have them. We don't have the precision. So the smallest representative positive number is 1.000 times 10 to the power of minus 9. This makes sense, which translates to some small number. I don't care how small. But the question is it? Is it the smallest number we can represent? yes and no. We could say that actually we will denormalize the number and just say we can start with 0 in this one case. We will break the normalization if we have even smaller numbers. Or we might not, and we might just say, yes, we will always want the numbers normalized. This concept is, by the way, this concept is also in binary floats. There is also like an assumption that there is always a digit here, but it can be broken, and these numbers are called subnormals. Now, notice that the absolute difference between the two numbers we can represent next to each other is increasing with the magnitude of the number. But the relative difference is always the same, give or take boundary condition when we have to increase the power, right? Both of these numbers have the same relative difference to each other, even though here the difference is 1, and here it's 10,000, 100,000, right? Maybe 10,000, I don't know. It's hard. No, this is 100,000, right? So these are the two closest numbers that are representable at that power, and the relative difference is the same. Now, we have a bunch of issues in this design. Let's talk about them. So for example, we have positive and negative 0. Why? Because we said that we will store whether the number is positive or negative separately. So when we have 0, we can say it's positive, it's negative. Like, is this an issue? Good question. A lot of people don't like it. A lot of people think this is really like bad part of the design of floats. Other people say this is a good part of the design. If we have time, I will explain more about this, how it comes up. And we also don't have unique representation for 0. We have a lot of zeros, actually, right? We have 19 different ways to represent positive 0. And since we also have negative 0, we just double that. So we have 38 ways to have 0. So what do we do? There is a lot of things you can do. One of them is say, this is one representation that's canonical. Like you say, okay, so the one proper representation of 0 is 0.00 times 10 to the power of 0. Yeah, that's the canonical one. And then you say the other ones we can use for something. You can literally encode like metadata in there. You can say this computation has failed because you provided wrong numbers, or you divided by 0, or you did something stupid. Or you can just say these are invalid and you can ignore them. Both are fine. We are making a toy. We are not making like real binary format, float format. Anyway, the thing about the decimal floats is that they exhibit the same issues that we have seen at the start with binary floats. Like if you take decimal floats and you try to encode this computation, 1/9 times 9, it will not be 0, it will not be 1. It can't be 1. Similarly, if you say, oh, I have 10,000, I want to add 4, it will still be 10,000. And of course, you will again run into this, like when you add numbers, then it matters in which order you do this. The results will be different. Let's take a look at why. And we will start from this one because this is the simplest one. So why does it happen that 10,000 plus 4 is still 10,000? Well, what we get when we sum them actually is 10,004, which is, in our format, 1.0004 times 10 to the power of 4. But we do not have those digits. We have 3 digits only. So we have to do rounding. And well, if we do the rounding, 10,000 is closer to 10,004 than 10,010 is. So, it's simple. We just don't have the precision for this. So we fall back to 10,000. Now, why is 1/9 times 9 not 1? So if we do math, like real math, then 1/9 is 0.1 repeating. This means there is an infinite string of ones after this. It will never end. And if we try to take, like, this is a number that we can't do in floating point format, right? We can do this in fixed bit format, period. So we have to round it. And when we round it, we get 1.111 times 10 to the power of minus 1, or 1.111. And when you multiply that by 9, we get this, which is exact, like correct result for this multiplication, but it obviously isn't 1. It's 1 less, like this is the least smaller number you can have that's not 1, but it's not 1. And of course, finally, the difference between adding the numbers from like starting with the big one or the small one. So summing is done left to right, right? And so when we start summing, we get 10,000 plus 4 is still 10,000. We have just seen why this happens. On the right, we see 4 plus 4, this is 8. This is simple. We do have the precision for this. And when we add it again, well, 10,000 plus 4 is still 10,000. Again, the 4 is lost. But here, now we are actually large enough that we will have to round up the result. So this is 10,010. And so this is now different. Again, due to the rounding there. So to recap, float addition is not associative. Like in real numbers, it is, but in floats it's not, due to the rounding and the round off that we have to do. Same goes for multiplication, and so on. And floats behave weirdly or unintuitively, if you want, in any base. Doesn't matter whether it's base 2 for binary floats in computers, or if it's base 10 for decimal floats, which are also in some computers, or base 17 if you want. They will always have these issues with round off because they are not real numbers. You have fixed size that you can use. And of course, like all these issues are because you have the fixed size for real numbers, which are uncountably infinite. Now, do you have questions for this before we move on? Oh, well, let's talk about binary floats. So this is the binary floats are again fixed with numbers that have base 2 in their representations. It isn't important to really remember these sizes. This is how many bits we have for mantissa in different size floats or exponent. What's good to remember is that the mantissa, which is how many digits you have, grows a lot faster than the exponent, which is how big the numbers can really be, or how small, because you can also have negative exponent. And to give you an idea, this is like the positive maximum value you can represent. See that for 64 bits, we have like 10 to the power of 100. This is ridiculously large. For long double, it's even more, but I will also tell you later that you should not be using long doubles. Use floats or use doubles. So the issue with long double is that it can be either on some platforms it can be just double. It can be just double precision floating point number. On different platforms, it's extended precision floating point number, and which means that you get more bits in mantissa. And in even other platforms, you get actually like quad precision, which is 128 bits, and this is its own thing, and it's hard. It's annoying because it's different across platforms. Okay, now IEE actually guarantees the result of basic operations on floats. If you add two numbers on IEE platform, you have to get the same results. Same for subtraction, multiplication, division, also square root, I think, but that has its own bunch of issues that we will get to later. So, the results are repeatable. You can expect your results to be repeatable across different platforms, assuming you have the same initial conditions and you do the same operations, right? Now, okay. Now, this is very different from getting useful results, right? Getting precise, like getting the exact same results on different platforms doesn't mean that the results are actually useful. You know, when we look back to this is not useful result for us. But it's perfectly guaranteed that like my computer will do this, your computer will do this, you know, my phone will do this. It's just not very useful. So what can we do to fix this? How can we solve getting useless results? So this is not a perfect cookbook, but I will show you some basic tricks we can use. The first one that is you can use wider type. Do you have issues with floats? Use double. This is fine. This is simple. You can do it in 5 minutes, and it works most of the time. It works 99.99% of the times. And the last one is just academical, so we don't care. You know, let's go back to this example. This is, once again, like 20 million plus 1 plus 1 is different from 1 plus 1 plus 20 million. And this is in flows. What happens if you do it in doubles? The answer is, it's fine. Double doesn't have the precision to do this. So, you know, extends the bit width and it's fine. And long double, not fine. You can use it, but don't rely on it. The big issue with long double is that because it's different across different platforms, a lot of libraries that you might find will not actually support long double, because a lot of interesting operations on IEE floats can be done by basically casting the float into an integer, doing some bitwise magic, depending on what exactly you want to accomplish, and then casting it back. But if you don't know how actually big the long double is, or the representation it uses, you can't do this. And while floats and doubles are like pretty standard across the platforms, long double isn't. So, you know, go from float to double. Don't go from double to long double unless you really want to, like you really need to. Okay, let's move on. So another idea, you can, if you are doing addition and only addition, you can sum up the smaller number first. By the way, this is the naive option. You know, like if promoting to bigger type was the simplest, this is the naive option. It doesn't mean it doesn't work. It's just, you know, something that you don't have to like go and read special algorithms to do this, but you can do this. It works a lot of the time, and you are fine. Like again, you know, we take 20 million, add one, expect to get 20 million and 2. No, this doesn't work. But what happens if we add them from the smaller number first? Well, we get 1 plus 1 is 2, and 2 plus 20 million actually works. This is fine, because now like we have 2 numbers that are big enough that when we add them, we don't lose the precision. And of course, now there is the correct answer. This is again for addition. This is the Kahan summation algorithm, and this is the advanced option. You know, this is when you actually like open the book and start reading the algorithms and how you handle this. Now, the fun part about this, when you are doing Kahan summation, you need 4 additions or subtractions. You know, they are basically the same because floats, like you can trivially invert the float. You need 4 additions per each number that you want to add to your running sum. And it doesn't fix everything. But this is like interesting example. If you have like something like this, like 1 plus huge number plus 1 minus huge number, you will still get 0 with Kahan summation. The issue is that like the Kahan summation to not be completely insanely expensive to compute assumes that your running sum is meaningfully bigger than what you will add next, which here isn't. Like here, this isn't really bigger than this, so it will fail. Now, you can fix this. There are modified algorithms for adding floats that deal with this. They are even more expensive. Like the simple fix for this issue, to get 2 here, what happens is that you add branches to do summations. So now you have like 2 branches and 4 additions per each like summand you want to add, and some comparisons, and it's terrible. By the way, fun fact, if you invert the logic of adding the smallest number first here, and you instead added the biggest number first, then this will get the same result. This is why like going from the small number is the naive option, because it can fail like this. So there was addition. What to do if we want to multiply numbers and we want to have the result be numerically correct? Honestly, you are kind of doomed, because there isn't an algorithm to do this. That is just like, well, okay, so what you can do is you can try to normalize your numbers to be around 1. Because 1 is good, there is a lot of precision around 1. So, if you multiply the numbers there, this is good. And then you denormalize the result back. You can't do this all the time. You can do this sometimes, but not always. So, you have to do something, hope for the best, hire someone who's really good at this numeric stuff to figure it out. And yeah, so this is one option. The other option is look for different formulation of the problem that you are having. For example, I used to do a lot of stuff with probabilities. So I would have this string of like 100 or more numbers that are between 0 and 1. And I needed to multiply them all together to get the final probability of an event happening. So what do you do? What do you do? Well, you take the logarithms. This gives you pretty nice reasonable numbers, and you add them. And adding is good. We know how to do adding. So you add them with good precision, and then you just exponentiate them back into the probability. This is good, but this is problem specific. You have to look for problem specific tricks if you need exact multiplication. And of course, as I said, IE does not provide you any guarantees on transcendental functions. The moment you want to take sine, cosine, logarithm, which I already mentioned, you have an issue. You have no guarantees that the result will be correct, exact, or repeatable across different platforms, at least in the, let's call it, base IE that you get. Now, what you can do, in this case, is use CR math, or correctly rounded math. There is a bunch of libraries out there. I think the most popular one is Core Math, but put a correctly rounded math library into Google, it will tell you a bunch of stuff. And the idea is that they implement the transcendental functions, their sines, cosines, and so on, in a way that they guarantee that the result will be like the proper result correctly rounded. So the idea is that it will take the number that you give it. It will make magic happen as if it did the math in real numbers, not in floats, and then give you the closest representable float to the correct result. This is actually very useful if you need either good numerical stability for these functions, or if you just want them repeatable between different machines. One more note to this. Obviously, they are slower than if you do this simply without any guarantees. They are often very interesting in the complexity of implementation. I looked in the core math sign, and it's like 5,000 lines of code just to handle all the different cases. Now, to recap. So basic math operations, reproducible on all platforms. They will always behave the same. Numerical errors, if you know what you are doing, you can fix them. And the simplest approach always is to just use wider float. And transcendentals are hard. If you need sines, cosines, logarithms, it's hard. Now, let's talk about comparing floats. So there are 5 ways you can compare two floats. You can just bitwise compare them. You can just take mem CMP and see if they are the same. You can do direct comparison. This is what happens when you write A equals B in your code. Note that these two are different. These two are not the same. You can compare them by margin. You can compare them with relative epsilon, and you can do ULP comparisons. Let's talk about it. So bitwise comparison, this is checks just the bit representation. Now, this is Again, not the same as if you write A equals B. Not the same. Important difference. And under this comparison, the two zeros are different and not a number. The error values might be equal, or they might not be equal. You don't know, because there is a lot of, you can have different, not a number, you can have different errors. So are they equal, are they not equal? Depends. Direct comparison is what you get if you write A equals B in your code. And under direct comparison, the zeros are equal. -0 and 0 are the same. And not the numbers are always different. This is like fundamentally guaranteed part of the standard. Not a number is not smaller than a not a number. It's not bigger. It's not equal. It's not unequal. It's not. Look, it's not. Now, this is useful in some cases. Like if you have like two implementations of the same operation and want to check that they give the same result, you can just compare them. Are these numbers equal? But most often it's a mistake. So let's talk about margin comparison. This is when you check that the difference between the two numbers is smaller than some fixed margin. Now, the advantages of this is easy to reason about decimally. I can say, oh, my margin is 0.5. So if the two numbers are equal under margin comparison, it means they are at most 0.5, whatever, different from each other. This is good. This is easy. And it works around 0. You can just, like 0 and 0.1, they have some margin that's reasonable. This is good. It does not work for large numbers. This is direct comparison for large numbers. Why? Because if you add like half to 20 million, you don't get 20 million and a half, at least not in floats. And of course, for doubles, there is the same issue. It's just way, way, way bigger number that you need. Yeah, so, this is like what you should know about it. Now, a little fun fact about comparing floats. So this is what I wrote as the margin comparison. And this is a different way to write this without absolute value of the difference. Not the same result. This and this will not give you the same result. The issue is that the top one will say the two infinities are different. The bottom one will say two infinities are similar. You can pick which one you care about. Like if you want two infinities to be the same under any margin, then you want this. If you want infinities to be different, then you want the one on the top. Anyway, so relative margin comparison, this is a way that you can say, okay, but I am comparing big numbers. So let's fix it. I will say, okay, is the difference between the two numbers smaller than some factor, like say 1% of the bigger number? You can also say bigger or smaller. Of course, the small using min is stricter. Anything that's equal here is equal here, but not vice versa. This is just a detail. Now, the advantage is that this is, again, easy to reason about decimally. If I set my epsilon to 0.05, then I am saying these two numbers must be within 5% of each other. This is easy. And it does not break down for large numbers. I can easily say 5% of 20 million in floats. I will get meaningful result. It doesn't work around 0 because, 0 times 5%, 0.1 times 5% is something smaller. And I will if one of the numbers is 0, I will never ever get them together. Like you need to take the relative epsilon of more than 100%, and that's meaningless comparison. Now, let's talk about the best one, except it's not. So it works on units in last place. So the unit in last place is how many steps are there, like the smallest representable numbers are there between two numbers. I will show this with an example. Like this is the same number, so the distance is 0. Here we have moved exactly one step to bigger number, So their distance is 1. There is no further representable number between these two due to our lack of precision. And similarly, when we just go way bigger, like now we are in like 10 to the power 7, but again, this is just one, there is one step between them, although like here the difference is 1, here it's 10,000, but this is just one step between them. So the distance is again 1. Of course, there's an open question. What's the distance of minus and positive 0? Look, I don't know. Figure it out. It depends on your tooling. Like there is different tools assign different distance to positive and negative 0. You have to check what your library does. And so the comparison says the two numbers, under like the ULP comparison, two numbers are equal if their distance is less than whatever constant you have picked. Now, this is great because it handles both 0 and large numbers gracefully. You say, I want to be within 2 steps of the target. This works for 0. This works for 20 million, 100 million, whatever. And you can actually really easily reason about this numerically. You know that like multiplication can introduce at most this much error in the units of last place and so on. So you can say, like, I know how I computed this value. It must be within 3 units of last place of what I know is the correct result, because that's the most like inexactness I should be able to introduce. This is good. What's the issue? Well, try to reason about this similarly. If I tell you like these two, like we are within 5 ULPs of the correct result, what do you know about the distance between what I computed and the correct results? Like intuitively, you don't know. Like you don't know anything because it's really actually hard to imagine what it means. So to recap this, yeah, you can't, there is no one rule to compare floats. You know, like that, a lot of people will tell you, oh, just like use epsilon of the bigger number and compare this. No, it will break if you use small numbers. If someone tells you, oh, are they like close enough? It breaks for big numbers. So you have to understand how to compare floats. What floats do you compute? What results do you get, the magnitude and so on, to pick the right approach? Now, direct comparison, usually a mistake, might not be. And of course, if you go with ULP distance, you need to understand how your tools handles like the distance between 0 and negative 0, positive 0, and similar things. Okay, questions for this? Yes, Martin?
There will be distance defined for numbers with different exponents.
Yeah, of course, it's defined for numbers with different exponents. And it's just how many steps you have to go. You can forever step to like, so the distance between two ULP distance between two numbers is how many steps you have to take towards like from one to another to get there. And if you cross exponent, that's fine, because like this is perfectly defined step. It just means that one step is bigger.
The distance between 1.999 to 2.000. Oh, that's not how that works.
No, but like
if you take the largest number with exponent 7 and the smallest number with exponent 8, the step is closer 1.
yes, if you cross exponents, but like it's the two numbers that are next to each other, the distance is still 1. Okay, now let's talk about limitations on what we have just learned on reproducibility, because there is actually a lot of them. So you know, you can be on platform that doesn't do IEE floats. Nothing we have learned is applicable. You know, this is IBM. IBM still has their own floats, and they default to them. They actually support IEE floats, but you have to explicitly go and enable them. Now, IEE platforms may also cause issues. Fun one is that when you are compiling for Intel CPUs, well, if you are compiling for x86s, and you do not enable SSE2 to be used explicitly, then your code will probably use the old FPU, the x87. And the funny part is that it computes internally with extended precision in 80 bits. But when you have to store the number, say on stack or to pass it to function and so on, then it has to truncate into 64 bits. So based on how you use the number, whether the compiler decides to flash it into memory or not, it will be done in different precision. So even if you have like the same set of steps for two initially same numbers, depending on whether the compiler just does all them all at once without truncation, or flashes them to memory from the FPU, you will get different results. So moral of the story, use SSE2 for your floats. This sucks. But, you know, languages also make this hard. So, for example, Go or C++, both of these have some issues about this, like IEE and think and compilation time evaluation and so on. Let's start with Go, because Go does its like own things with constants. Okay, this is a very simple Go code. You know, all it does is sets a to minus 0.0, and then it is supposed to print a and 1 over a. Both of these are defined in IEE and have results that they should give you. What's the result? 0 and plus infinity. So, okay, let's like let's delay like 1 over a, and this is just, okay, maybe this is it. How do you go from negative 0 to 0? Well, Go, because it's, you know, the smart language for smart people, just goes, actually, in constants, we'll use real math, or as close as we can get to it. So if you write this, it just goes, no, negative 0 is stupid. You can't have negative 0. So it just writes in 0. Literally, the Go compiler goes, erases this minus, and compiles the code. Oh. And since it's 0, then this plus infinity makes sense. Now, C++ does this a little bit better. It's not quite as weird about it. You know, okay, again, simple snippet. We have lib. We write double, negative 0, and negative infinity. And then we print the results. What does this do? This gives us the correct result. This is fine. Now, let's do this in compile time. Const x per double. Const x per like double. So what happens? What's gonna happen here? Any guesses? No, it's compilation error. So const x per tries to stop you from doing undefined things. So this means, oh, but you are dividing by 0. This is undefined, and so it, you know, can't happen at compile time. But this is IEE. This is not undefined. This is perfectly reasonably meaning. Yeah, so anyway, you can break the predictability with compiler flags. Now we are just purely in C++, right? Okay, so we can say for fast math, this says ignore IEE, optimize as much as you can. You know, for MSVC, this is for fast. Oh, fast. This implies a fast math, because of course it does. Why wouldn't it? Now there is some fun flags like fun and safe math optimizations, you know, bunch of them. Nothing. Beware, okay? Yep.
Is the third one supposed to be fun, safe?
Of course. Of course it's fun and safe. It says so in the name. No, okay. Beware. This is really infuriating, GCC fact. If you say, oh, fast, but no fast math, you get fast math anyway, because screw you. What do you know? GCC. I didn't actually check Clang because this was too depressing to try. So, but, you know, maybe you compile everything properly, but external code can still get you. You know, someone can write function like this and just go, oh, but I'm going to change the floating point environment and say that we are now rounding the numbers differently. And just never reset it again. Done. After you call this function, everything has changed. Because floating point number rounding is global for some reason. I mean, the reason is obvious. It's legacy. It was like...
Also between threads or threads?
I think it's per process. Now, fun linking against external libraries can also break reproducibility. This is the most fun one here. So let's have this simple function. You know, this is FPC for FP classify. We call this magic function, which returns some value based on what this float is. Like, is it 0? Is it subnormal? Is it just some float, whatever? Infinite, it also returns infinity and so on, but we don't handle this for this example. And we have tiny little byte that just writes 2 numbers. These are the smallest possible positive numbers in double. And we print them. You know, we print them their value and what their classification is. Okay, everyone with me? So just compile it normally. You know, O2, test, run it. Result is it's subnormal. This is correct. Now, if you do fast math, it starts getting weird because it still classifies the first one subnormal properly, but the second one is 0. Does anyone know why?
Fast math design was subnormal.
Kind of, but the real issue, like, this is volatile. The also time is volatile, so it's forced to be reloaded. And the reload breaks the handling in the function, but not like the print constant. I don't know. Look, compilers. Good. Okay, O fast, again, we get the same behavior. This will be fun. So we say O fast, but no fast math. We get different behavior again. Not only like this doesn't disable the annoying parts of fast math, this gives us another thing it does, different from plain fast math and different from just from O fast, different from fast math. I don't know. But you know, let's go back here. Just compile things normally. Let's make a library. We will make the world's stupidest shared library. One file, it's empty. We compile this shared library, position independent, blah, blah, blah. Oh, fast. This is important part. Okay? No, this flag will be the devil. And we want it to be called libempty. Now let's compile our test code again. So we compile it O2. No O fast this time. Test CPP, yeah. Name it test. You like link from the local path, link the empty library, and to change run path to origin so that when we run the binary, it will look for the libraries in the local path where it is. Okay, let's run it. But we didn't specify O fast or fast math in our compilation. What happens is that this was propagated from the dynamic library that's empty.
Does this happen for all the flags, or is it just
It's just the fast math and O fast. Like if you do fast math or O fast, which implies fast math, this happens. At least unless you are using GCC 13 or newer, which, you know, I think it's this year. So, you know, for the last 30 years.
Can you actually check if the library you're linking against was compiled with these flags?
You can do it indirectly. You can load it into some process and then check what happens here.
Yeah, I mean, I'm thinking like how is this in a store code?
Yeah, so, okay, what's happening? Okay, what's happening is that when GCC sees, oh, I am compiling this with fast math, it links it in special object file. It calls it CRT fast math. And that object file does one thing and one thing only. It has a global constructor. And by constructor, I mean the GCC extension to assembly, not like C++ constructor. That just changes the global FPU state. Yeah, the first thing that happens when like this is loaded is that it executes a bit of global code that changes the global FPU state. Well, the good news, GCC 13 does not do this anymore. Clank might finally stop doing this year as well. They didn't want to change before GCC changes this, and there is an open pull request to fix this since February. They ran into some issues where they found out bugs in their handling of the different contracts and now want to fix it before merging this. MSVC never did this, okay? If you are using MSVC, you are safe. Okay, let's recap. Yeah, you have to know what your language guarantees gives you. If you are using Go and you write -0, no, you know? Okay, compiler flags can break IEEE 754 guarantees. external code can break your reproducibility, even if you just link it and never execute anything. Literally, empty library can break this. Questions for this? No, okay, and yes.
If they remove this CRT, blah, blah, blah.
Yeah.
Doesn't it mean that the execution will be a little slower?
Yes. I don't care. I don't want this in my code.
But like, I always assume that I have imprecisions everywhere because if you are working with real physical data, it's pretty normal that you know that you have only 4 valid digits and you have to count on that all the time.
But the issue is that, like, okay, so how do you account for this is the issue, right? Because what happens here is that, okay, so you know that you have like your first digits, first 4 digits are valid of the inputs you have, and the rest is some noise. If you start doing math on this, and like what the math that you are doing actually does changes under you, then you are screwed again. Because if you say I have these tolerances, if my computation is done the way I've written, then if someone goes and changes what you have written, then you don't know anything about your tolerances again. Like people who have supercomputers don't use this, like, because they want their results. Okay, yeah, we still have some time, so let's have one party trick. I said that more bits are better. I did say that this is like 99.999% of the time. Let's look at when this doesn't happen. Let's actually look at a simple recurrence. So we have first point, second point, and every new point is computed like this. Yeah, it's like, look, I am not doing this from my head, but it's easy. It's not terrible, because all of these numbers that you see here can be represented as floating point number with some minimal precision. Like if you have 8-bit floating point number, all of these numbers are exactly represented. Now, if you do this in real numbers, the convergence point is 36. Okay, trust me. If you want, you can do this math, but trust me, it's 36. Now, what is it in floats? Let's have some code, This is the recurrence written as templated function, so we can try different floating point types. The first iteration, second iteration, and this is exactly what we have written on the slide before, and then we just ask the result to be printed. Okay, everyone trusts me that this does the iterations properly? Yeah, I'm going to assume yes. So let's run it for floats. 36, this is good. Let's run it with doubles. And this is not good. We actually get the correct results for a short while, and then we just go to 42 and stay there forever. Let's try long doubles. These are correct again. So what's happening here? What's happening here is actually a party trick.
I think the numbers are just so carefully crafted to make sure that specifically the rounding will happen. That will cause it to go wrong and reach some stable point that's elsewhere we want.
That's 90% correct. So if I go back for a second, this recurrence has 2 stable points. An attracting stable point, which is 42, and a repellent stable point, which is 36. Right? And yes, that was just happened to get the wrong results for this. But this is not they are not picked as uniquely as you might think. If I pick different starting points, here is a bunch of them. This is what happens for the different types. Notice that sometimes, like float always gets it right for this set. Doubles sometimes, long doubles sometimes, and it's not exclusive. Like here, it seems that they switch, but here they both get it wrong. And also notice that these numbers, again, they are all easily representable in fairly reasonable short floating points. So what's actually happening is that the rounding in floats is imprecise enough that you can't go away from, that you don't get away from the replacement starting point. This is actually a very interesting result if you are an academic doing numerical computations, because it means that like the small floats have some regularizing effect on your computations. But for us, this is like nice magic trick. You know, you can do this when you want to win some argument and say, yeah, no, like bigger types aren't better. So, you know, magic trick, but like wider types are almost always better anyway. And that's the end. I am going to open it for more questions, but I want to give you these two more pieces of fun facts about floating point numbers. Because people often wonder why doesn't compiler optimize this? Why doesn't compiler optimize x plus 0.0 is just x, or x times 0.0 is 0? And the answer is it can't, because these are not valid identities in floating point numbers. So, questions?
Yes, I have a question.
Yes.
Can you open the Mozilla report from the GNU compiler? I have a question for one of the, if you have it online answer.
Yeah,
Yeah.
in Zoom chat, we can. I mean, if you want to share it on the screen also.
Sorry, but what? I might have missed something.
Yeah, just go. Yeah, this was before you arrived, so just go to Zoom.
No, to Zoom? Oh.
Yeah,
Uh,
and in chat.
yeah, chat.
Yeah.
Okay, I'm going to take a look at this later.
No, no, I think like if you wanna. Yeah, maybe move it on the screen so others can see it. Also.
If you go to comment number 8, and maybe increase the font so that everybody can see.
Number
Number
8 and make it bigger.
Yes. So this is a program I have written, and depending on the compiler options and the compiler, it produces different results.
Yeah.
Yes, and my question, what would these compiler options do?
Okay, so MSSC2 means use SSC2, assume it's available. Okay, I'm not sure about this one actually. Isn't this supposed to be SSC2? Because like, so I don't actually know this option, but like at a guess, it means for floating point math, use SSC. And I would expect that this is supposed to be SSC2 actually. Like, because SSC1 does not cover all of the floating point operations you might want to do. And I know that, for example, the math SSC macro specifically is like explicitly separate SSC1 and SSC2.
But what's the difference between using SSC and not specifying anything?
So the difference should be, again, like, you know, I have just seen this, but so the difference is that SSC1 does not have support for all of the floating point math operations you might want to do. I can't tell you whether like this is in there or not. So if you can't emit some an SSC instruction for some of the operations, you should expect the FPU, the x87 FPU to be used instead.
It is, but only for 32 bits. For 64, it's not. If you mean this 80-bit area that spans integers.
Yeah.
Because I think that M64 implies SSC.
Yes, but you know, you might still expect that like this could override. I don't know. Look, if you can disable fast math from fast, why do you expect everything else to work?
And what rules does this exact precision standard do?
I actually don't know that.
You can scroll down.
I would have to look it up. Yeah.
And this exact precision fast, is it the same as FastMap or it's different?
This is a subset of FastMap. That one I can actually like answer. Subset. It's small part of it. I can actually like. If I go no. I need to go back to this window. For the other window. Jasně, protože to je jiný. If I go back to compiler flex, like FastMap implies this one, and another 4 or 5 flags that change how the math behaves in the compiler. So like it's small subset of it. And that's all I know about this.
Can you go back to that?
Yeah. Give me a second.
If you scroll down to comment 11. Now here, because Clamp and compiler can behave differently, I have written that there is a problem with the GNU compiler. And comment 11, it contains this code, and this code proves that the problem is with Clamp. What does this mean?
I don't know. So, okay. Float, eval method. Long double mantissa link. I actually don't know what this switch does. Like what this macro, what this macro means. Yeah, it's like weird. I can actually look into this, but no idea.
Okay.
So it's in the chat, right?
Huh?
It's in the
Yeah.
chat. Okay, I'll take a look at this because this is interesting. Yeah, that's true. Okay. Interesting.
And I usually I wrote a paper that some math in the GNU compiler is wrong. And because other people have also written the same, but they always say this is not a bug, this is a feature.
Compilers do what they want. You can say they are wrong, but like you have to deal with them at the end.
That doesn't change anything.
Okay. Anything else? Yeah.
When you mentioned that linking to an empty library also links CRT fast math into the executable, is there a way to detect this behavior, for example, by loader or when you load at some point? At least?
Yeah, I mean, like you could scan the code in the dynamic library because it's it's pattern that should be easy to find, but not like you can't like detect it from the code.
On target, right?
Sorry?
You need to do it on target because it then also depends on what you load at runtime.
Yes, if you mean like yeah, you would need to be on the target to have full understanding of what you are linking in. Like this.
LVD wouldn't show you this way. right?
So it's not library that we load it. It's compiled. It's object file. It's compiled into the library. So
Okay.
it's not separate library. Yeah. LDD won't tell you because it's not separate library. Yeah, you like this, like the code that happens there should be fairly easy to find because it's very, not many things change the global FPU options, and when they do, you still want to know about it. So you can say like flag any library that does this. Okay, anything else? Then
What are these Wuhan summaries? You said 4 numbers, but what do they stand for?
Kahan summation. No, like, oh yeah. Do you mean Kahan summation?
Huh?
Do you mean the Kahan summation?
Yeah, what does it mean? I had converted it before.
No. Binary floats. Okay. So it just does small additions. What's actually happening is that instead of just keeping the running total of the sum of all the numbers, you also keep basically an error variable that says what was the rounding error from adding the last 2 numbers, and you then use this to compensate the final sum, either up or down, or this is
What's the
no, I mean,
let's say this way, what's this Kahan summation?
yeah, let's just, oh my God, what's this? And like, this is why I don't understand why Microsoft does has news, because it's always some stupid bullshit. But okay.
1991, something happens. Should I care?
Yeah. So yeah, so it looks like this. This is like probably the simplest way to show it off. Might be a bit small.
Oh, you see, fine.
Yeah, but we are also the closest. And so what's happening is that instead of just adding the number always to your running sum, you also compute factors that you can use to recover the parts that you discarded, like the low bits and so on. And what can I say? Yeah, the cost is, actually 4 operations here to get the result per each number that you want to add. And if you then run into the big issues and you use, different algorithms, announcements, yeah, like this. Now you have an issue because now you are branching, and this is no fun when you have to start branching, and then you have even more complex variants. And you are branching here, and you are now paying lot of costs for precision.
You convert this to branch bus?
Probably, but you would have to evaluate both sides of the branches, and I'm not sure that would actually be cheaper. Yeah. Okay.
Perhaps more of a practical question with using floating point numbers. So let's say I have a ray tracer. I have a problem. I need to find an intersection with an object in my scene. When I move my camera far enough, I start to get the so-called acne points, which means that I find imprecise intersections inside the objects themselves, and the light does not get it. So I do a stupid thing, and I add some kind of delta to it, an arbitrary delta, and I get those points outwards a little bit, so that I account for this imprecision. But let's say I am just a stupid programmer. I don't know any math. I just want my intersections to be precise enough. How do I calculate an arbitrary value and know how much imprecision I need to account for?
Oh, you can't do that easily. So like, if you are doing this in floats, then my advice to use wider type is the first one. Because, so if I answer correctly, if you like move away the camera, then you have issues that the intersections start being incorrect, because, you know, now you are dealing with the big numbers, and the step between the two values that are next to each other is too big for what you are doing. Yeah, this is not easy. So one thing that you can do in cases like this, but again, like it's not something you can just do simply, is rescaling. You basically say, okay, but what if like what if I don't just count the like origin, you know, naively, but I just basically you find that you have to adjust the distances, how we calculate them, so that they are smaller, and you get the intersections back again. And this is usually done by basically moving your origin closer, and then accounting for the imprecision you get from the like recalculated origin to actual origin. Okay, once again, any questions? Then I think I can call it and say that we are done.
What do you use for presentations of this web server?
It's old version of Reveal.js.
What?
Reveal.js. Reveal. REVEAL, like show or reveal. JS. Okay. Share. I don't want to share. I want to stop sharing. I'm done.
Yeah.
And begin the liquid option.